generalized topic. I will cover this, but together with another one to have a bit of broader view on basically systems that are driven out of equilibrium in a stationary state by driving them with lasers and coupling them to different sorts of bases. And the motivation that I want to draw here comes actually from this from a different community, namely people thinking about active matter. So what are these systems? Yeah? So these are systems with many internally mobile agents. Yeah? Think of a flock of birds, or a colony of bacteria, or even systems like a traffic flow. And what these systems all share together, in very loose definition, first of all, they have emergent collective behavior. I think that's pretty nicely visualized in this flock of birds here. And second, these things here do not obey the principle of detailed balance on a microscopic level. Yeah? So in these systems, this is realized by these agents being self-propelled, yeah? So they can move by themselves, and that is brings in a notion that at each point in space, yeah, a detailed balance is broken. And I want to basically ask the question whether and how we can have scenarios of active, condensed, or synthetic matter. Yeah? So here, I think we are not lacking this point number one, collective behavior in solid state or synthetic matter systems. And recently also quite a portion of platforms is moving into this direction of breaking detailed balance on a microscopic level. So that technically we are speaking then about driven and open quantum systems in here. I mean, we have examples from solid state, cold atoms, or quantum devices. Say a very prominent platform in the solid state context is these light-induced superconductors. So there, the idea is to take a piece of matter and Floquet drive it. Yeah? So because a piece of condensed matter also has decay channels, yeah? Like phonons, or you can couple your electrons to phonons, so that realizes an instance of a driven and open quantum system. Another platform is where you replace the classical light driving with even a quantized light, yeah, by putting, say, a piece of material or also a system of ultra-cold atoms into an optical cavity. Yeah? So then you have quantized light that speaks to 100 degrees of freedom and that drives them. Or in these NISC, noisy intermediate scale quantum devices here. Of course, the long-term goal is to implement a controlled, unitary dynamics, also a driven one, a time-dependent one. But, of course, at the moment, these systems suffer from all kinds of decoherence, so that also makes them kind of driven and open systems in the class of what I want to discuss. And the questions that arise there are basically maybe twofold. Yeah? So first of all, are there any new phenomena, new states of matter that you cannot have under the circumstance of thermodynamic equilibrium? And of course, I mean, given now these systems are made of quantum ingredients, whether we can really pinpoint some true quantum effects or whether this is also always lost. So to refine this question a bit more, so what we want to study is systems where on the microscopic level detailed balance is broken, and then we want to ask whether this can give rise to universal long wavelength non-equilibrium phenomena that you would see in the lab on the probing the system at a macroscopic scale. And I mean, the basic logic is sketched here. Given a system on the microscopic scale, some reference system at equilibrium, I want to push it out of equilibrium, for example, by some laser drive or so. And then the question I want to ask whether, I mean, we face a situation where the loss of memory of this breaking of detailed balance actually happens, yeah? So that at large distances you would go back to equilibrium. That's really what happens generically. Yeah? So here's a light-driven piece of matter, but it's extremely well approximated under equilibrium ideas. But as a matter of principle, you can't rule out the opposite scenario, yeah? So that, in fact, a real non-equilibrium state of matter ensures. And one basic ingredient that we will always need here in order to study this behavior here is the talking to soft modes. So that whenever you have soft modes, that could be critical modes, Goldstone modes, that is a circumstance under which basically under coarse graining, under RG transformations, you really get a non-stopping RG flow, and then it could happen so that the system finds a fixed point far from equilibrium. So let me give you one example where this works concretely, so to give you a bit of idea of the setting. So here, this is an exciton-polariton system. You have a semiconductor hosting these excitons here, and this is immersed into Bragg mirrors. So you have a light coupling to these excitons, giving rise to so-called polariton degrees of freedom. So, and the phase of these polariton degrees of freedom actually shows a KPZ scaling behavior. So this is, I mean, a kind of behavior that is not so easy to achieve at equilibrium conditions. So here we have indeed some instance of this type. If we compare an atomic BEC system, people thinking about cold atoms, so that's an equilibrium system with equilibrium long distance properties. And these polariton BECs, so they are light driven and actually choose to converge to a fixed point, to asymptotic behavior that is within a non-equilibrium universality class. So for today, I want to focus on, as I said, two specific aspects. The first is basically the physics of time crystals. So that's a limit cycle behavior. That's a kind of circumstance where non-equilibriumness jumps into your face. When something is rotating, that would be a perpetuum mobile if that would happen at equilibrium. So, and that what we did, we analyzed in much more detail the nature of phase transitions for the onset of a time crystal, and found that this gives actually rise to far from equilibrium universality classes. So again, indeed a fixed point without equilibrium counterpart. We also looked at the ordered phases, where in a time crystal you break a time translation symmetry, and we thought about the Goldstone modes of that. And if I have time, I will also mention a bit platforms where this can be seen. And as a second part, I want to discuss an idea of seeing quantum critical phenomena far from equilibrium, where detail balance is broken by developing a fermionic analog of absorbing state phase transitions of direct interpolation transitions. So this first part is done in collaboration with my postdoc Romain Davier, PhD student Karl Zeller, and my colleague Achim Roche in Cologne. So I hope this resonates with the audience. We take this effective field theory approach here, where on the microscopic scale, say if you have a solid state system, the degrees of freedom are electron, spin, lattice vibrations. All we need to know about that for this approach here, we want to know the symmetry. So here I've listed those for specific systems that can be driven out of equilibrium. It can also concern symmetries like external symmetries like time translation, space translation will be important along this talk. But what we want to make sure that the detail balance is broken in these systems. Then, we assume, or we think, we have some reason in these systems to say that there's a collective effect, there's some condensation phenomenon going on, and we'll also assume we understand the symmetry breaking pattern, so that is of course case by case. And then in our minds we'll do this kind of coarse graining to pin down an order parameter field theory with broken detail balance, and the work is then actually to extract really the long distance universal physics that is governed by the soft modes, which as I said could be Goldstone modes, critical modes, or the like. So for this talk, I want to introduce this order parameter field theory, identify phenomena in this framework, and then maybe later go back to the more microscopic way of thinking about the system. So let's discuss this order parameter field theory first, and I build it up gradually. So we look at this mesoscopic scale, understand the symmetries of the problem, so let's do something very generic. Let's look at an ON order parameter field theory already at equilibrium, kind of a workhorse. And the most basic version you can write down is this relativistic ON model, inertial time derivative. And here we have a phi 4 potential that for this R parameter negative can show ordinary spontaneous symmetry breaking, where this rho here is the invariant combination for this order parameter under ON transformations. Let's now add dissipation to the game. I mean, that was so far a deterministic evolution. Now, in an open system, we always have some dissipation going around, so that's really the damping that you also know from a harmonic oscillator with n components. And we also know that, I mean, whenever we have a dissipation, there must be some fluctuation to preserve probability in the system. That is done by this stochastic force here, this noise that allows the system really to explore all configurations beyond the single deterministic one. And by the way, if you would drop this term here now, then you arrive at these Halperin-Hohenberg model A without conservation law. So that's another point where how this model connects. The key point will be now to break detail balance, break the equilibrium condition. So that's something that was also said several times in this conference here. The condition of thermal equilibrium can be encoded in a specific symmetry, so thermal or KMS symmetry. And without showing you this, so you can believe me that these two terms here, they are violating this KMS symmetry explicitly. So another word of saying is that these represent non-conservative forces. Okay, and now this model here, that's now complete. We have the space degrees of freedom in particular, and you see there's two key parameters, with which you can drive phase transitions in this problem. The first is this R tuning parameter that's really triggering the usual ON phase transition. And then there is a second parameter, this gamma, which basically I argued is the damping rate of this problem. Now, you can also arrange in an out-of-equilibrium system for an anti-damping, putting it to negative values, and that only is a stable situation at equilibrium. That you can see it from the fact that this, I argued, is a non-equilibrium nonlinearity, and that can compensate the instability that pops up when you go from damping to anti-damping. And that actually triggers limit cycle behavior. So that is all shown here in this phase diagram. So first thing, let's do something very simple. Drop off all the complexity of this problem. Yeah? So like no space dependence, no noise, just a mean field phase diagram to begin with. And you have then these three phases in the plane of these two relevant parameters here. So we have a disordered phase. We have an ordinary static ordered phase here for positive gamma, for damping, not anti-damping. The system orders by singling out one direction here for n equals 3. But when we go to this anti-damping regime, then the system chooses to develop a orbit. So, or, I mean, a time-dependent, periodically time-dependent solution, and that is, I mean, clearly a non-equilibrium effect. So if you would see something like that at equilibrium, you would indeed have a perpetuum mobile. Okay, so one more detail about this model here for later convenience. So there's also something interesting in the sign of u minus u prime. So now speaking about this ordered phase here, it can come in two flavors. Namely, we can have for this sign here, we will see actually the order parameter basically going up and down, oscillating. So this is something you can also have, I mean, that is known from van der Pol theory. Basically, for n equals 1, this is the van der Pol theory. Then you can have an oscillatory solution. But, I mean, for n larger than 1, you can also have this rotating solution, and that's really basically the sign of these nonlinearities. So in this way, I mean, in terms of symmetry breaking, here we're singling out an axis, like in static symmetry breaking. There we're singling out an orbit. So that for example, gives you different types of
Can I ask a question about the, yeah, maybe, well, I guess the previous slide, but it was similar to the one you just saw. So what kind of time dependence do you get? Should I think of these as your field as moving around the bottom of your potential?
Right. Yeah. For example, for n equals 2, it would be just something like that. Okay. Yeah, so that's
just like a generalization of that.
Right. I mean, for n equals 2, yeah, you have a plane. Yeah, so you just have a circle, okay. And then the thing starts to rotate in a circle. That's what happens, for example, these exciton polaritons. Okay. And now for n equals 3, for a magnet, you could have this behavior, yeah, really depending on the sign of u and u prime, where the system, I mean, develops either an oscillatory behavior or a rotatory behavior. So it traces out a cycle. There's a single scale generated in this problem which tells you the speed of this limit cycle. Mm-hmm.
So in order to get this time crystal behavior, I thought you would also need to drive it like you do in a Matthew equation. You get this without any driving? Or?
Yeah, no. I mean, I'm saying that the basic condition, yeah, to have this behavior is to push the system out of equilibrium. Mm-hmm. And you can do this, the fun point of this effective field theory is you can do this in many ways. Okay. I would agree that on some very microscopic level of description, yeah, if I take a magnet and then I need to drive it with a laser really, yeah, so I drive it periodically, but in such a description we have coarse-grained way over the time scale of the drive. Then the system looks time translation invariant again. So this is not something that is protected under coarse graining. But what is protected under coarse graining is the fact that detail balance is violated. In other words, that the symmetry is gone. Okay. And so I'm building these theories just based on this single piece of information. Does it have this KMS symmetry or not? And here we're arranging for it to violate, and then there's nothing that would exclude, for example, this time crystalline behavior. And so in some sense you could even think, I mean, this very short, very fast driving on the microscopic scale transmutes into a larger, much larger scale of the oscillation of this limit cycle.
So is it, I mean, so you're saying that these two extra terms that you added, they violate detailed balance?
Yeah.
And is that easy to see that it violates detailed balance?
I mean, it's easy to see that, I mean, if you apply the symmetry transformation, that is not invariant. Yeah? Another way of saying this is that, I mean, that my equation of motion for phi cannot be written as the variational derivative of some scalar, real scalar function. That is not the structure we have here. We have some force field which is not conservative. So that's this notion of non-conservative forces, but it's basically the classical limit of this KMS symmetry gives you exactly this condition.
And is it easy to like physically motivate these terms? I mean, like I don't see.
All this equation here?
The two extra terms that you added.
I would say you can also look at it like that. These are the simplest terms that are compatible with the breaking. So think of this really effective field theory spirit. Yeah? So everything that is allowed will happen. So, and then of course it doesn't tell you, you have to have it be in a specific parameter regime to see this limit cycle behavior. Yeah? Just breaking equilibrium, yeah, that's everywhere here, but only down here we have a real physical effect of that.
Yeah. In principle, you could have more complicated dependence on rho in those terms, right?
Well, I mean, this is really the systematic gradient and low order in rho dependence. No, I would say no.
Well, classically, right? If you just look at the classical dynamics, right?
Yeah. No, I mean, this is the basic. This is as you do in ON vector models. You have a quadratic term that still has derivatives, and then there's a quartic term. That's really exactly the same. Yeah? So the point is that you allow then for u and u prime, but nothing more. So it's complete in this sense. It's systematic in. I mean, we take all non-irrelevant couplings into account that are compatible with ON.
So I know you're just doing mean field theory at the moment, but do you have any idea as to how the spin disperses as a function of time? At the moment there's a big vector that's processing around the equator, but presumably in a real system at a really, really long time scale, the probability distribution for that orientation starts to broaden a little bit.
Yeah, exactly.
Do you
Yeah, I mean, this is then, the next step will be analyzing the fluctuation effects, and exactly come to that there is something interesting going on from that.
Yeah, can I just follow up? I'm trying to reconcile what you're saying there with what I'm familiar with. So I usually think of a system at finite chemical potential as being one where the field is executing, like is rotating.
Mm-hmm.
Like it would be something like e to the minus I ut.
Mm-hmm.
But that's an equilibrium phase. So why should I think of this one as a genuine non-equilibrium configuration?
Right. I mean, there you can ask Masahito. He wrote a very nice paper about that. Yeah. So where they argue, I mean, that a chemical potential term is something that leads to an unobservable effect. Yeah. So in order to observe this chemical potential rotating, you would have to couple it to a different system held at a slightly different chemical potential to see a phase difference building up based on that. And this you can read it as, I mean, I have now two systems that are coupled to each other that are not chemically equilibrated. So, I mean, if in order to see this, at least, you have to go to a non-equilibrium situation.
I mean, but
and also, I mean, there is a little bit something. I mean, okay, so there is some things that one. I mean, that's more the initial state dependence. Yeah? If you have a conserved charge, yeah? So that's a chemical potential is a conserved charge of particle number. And I mean, then you have, if you insist on your Hamiltonian to write such a term, yeah? So then basically by the initial state and by the choice of the chemical potential, you get this rotation here. The limit cycles we think of, and that is indeed compatible with equilibrium. Yeah? So that's a slight, I mean, so to say, situation where something could look like a limit cycle. I want to argue it's a different effect. Eh? So it's the effect that the initial state, you fix the particle number is conserved, and then you have a limit cycle based on that. It would only work at exactly 0 temperature. At any finite temperature, you would have dissipation but here, the kind of limit cycles that we have in mind are of the different type. Yeah? So you run the system to stationary state, and this limit cycle really develops dynamically, develops out of the system. This is spontaneous breaking of time translation symmetry.
So you're saying you end up with the limit cycle regardless of the initial state?
Exactly.
In
Yeah.
the equilibrium case, you need to.
So it's really just a memory of the initial effect of the initial state due to a conservation law. It's a different physics.
So you don't need to be at 0 temperature, though.
We don't have to be at. Yeah.
Neither does the equilibrium example. You just need to be below the ordering temperature.
I'm not totally sure, yeah, because I I could imagine there is some decay. Okay, so
it's like scaling the system size, I think.
Yeah. Okay, but I think so it's really different physics. One is basically initial state and conservation law taken together. That can give you basically a rotation or precession in a magnet of this associated to the conserved charge. This here is a phenomenon that happens in stationary state spontaneously. So this is a spontaneous breaking of time translations that we have in mind here. Other? Yeah. Good. So these are these two types of limit cycles. And now let's zoom in more detail here. Yeah. So if you look at, and so what it means, we want to understand a bit more the nature of these phase transitions here. Yeah. So let's go for positive gamma. And then we find basically this little boring effect here. So if we take now fluctuations into account, we find that this line here, despite we broke equilibrium at the microscopic scale, flows to one of the famous universality classes for dynamical critical behavior. So model A universality class of Halperin-Hohenberg, and despite this breaking of Diehl balance, we find exactly the equilibrium exponent with no correction, nothing. Same fixed point. The other transition here is an order-to-order transition that goes from the static to the dynamic order that proceeds via a so-called critical exceptional point. And there, when you analyze this problem, you see actually there's a non-equilibrium fluctuation so strong that the system cannot sustain a critical state and instead develops a weakly first-order fluctuation-induced first-order phase transition. I don't want to comment on that in too much detail. That's not so universal. This final transition line is what is much more interesting from my view, because there we really see this behavior that if we push the system a little bit out of equilibrium, then I mean, we find a new universality class which is really as far away from equilibrium as it gets. So this, I want to discuss it in a bit more detail. And how you can understand this problem is built up here. So we now want to look at this transition, which goes at a finite scale r, at this oscillatory scale. So there's a finite frequency scale at this transition point, while we go with the damping rate through 0. So the renormalized damping rate is 0 at this critical point. But another scale is finite in this problem. So then it makes sense to think about how does the typical field configuration that I have to sum over in order to evaluate my dynamical partition sum, how does a typical field configuration look like? And you can think about it like that. There is a gigantic envelope with time scale 1 over gamma, which even diverges when we go through this critical point. Yeah? But inside this envelope, there's a very rapid oscillation that comes from the fact that we're having a finite frequency critical behavior. Yeah? So really by just looking at this picture. And that motivates us to parameterize all the field configurations we have to sum over in a way to separate the slow envelope degrees of freedom explicitly from the fast inner oscillations. Yeah? So our slow degrees of freedom for this transition will be these chi1, chi2, yeah, which oscillate which develop in time on much larger time scales. And if you then look at the symmetries of this problem, we see that, I mean, these chi1, chi2 slow degrees of freedom inherit, of course, the ON rotations of the original model, but they also acquire a new effective external transformation, an SO2, which basically is coming from time translations. Yeah? If I do a time translation here, yeah, say here, I start here, I end up here, a small shift. I have done a gigantic effect on this inner oscillation, on this fast degrees of freedom. I have basically done nothing on the envelope degrees of freedom, and therefore the net effect of such a transformation is just a rotation with angle alpha is omega naught times t in this new space that emerges for the slow degrees of freedom. So the upshot of this is that if we want to understand this transition here, we should not think about just the ON symmetric problem, but in fact of the ON cross SO2 symmetric model. And then you can go again in this spirit, and we write down all terms that are compatible with this symmetry group. And so there's this kind of invariant combination, there is another one. And what is quite reassuring is that, I mean, we can indeed, even also in this effective low energy model, we can recover both these phases that we've seen in the original ON model with the second order derivative. We can see these two phenomena here as well. Yeah? Depending, that's basically which of these invariants condenses. Yeah? So this determines whether we are on this oscillatory or the rotating branch. Now I play again the same game. Yeah? So this is the right symmetry group to analyze. Next thing, I want to teach this system to obey or disobey thermal equilibrium again. So this here is actually a pretty neat geometric visualization even. So if we insist on thermal symmetry, then all these couplings here of these two, the dissipative and the reversible coherent dynamics here, all these couplings are aligned. So that tells you that, I mean, dissipation and reversible dynamics are not independent, while the out of equilibrium situation is described by this scatter plot here. Okay, so that is now actually the kind of situation we want to look at. Yeah? We want to look at this ON cross SO2 model operated under non-equilibrium conditions. Okay, and so we did that. Yeah? So we looked at this ON cross SO2 in dimensional expansion to two-loop order. And for n larger equal 2, we find there is actually a new non-equilibrium universality class. And to explain this, yeah, I mean, in terms of the RG flow for this problem, that is a good figure here. So imagine there is this plane, the gray plane. On this plane, the theory obeys. This is couplings that are compatible with equilibrium symmetry. in this plane, there is a Gaussian fixed point. There's a known Wilson-Fisher fixed point, which sits here. But now we allow for couplings that violate this symmetry. And then you see, oh, there pop up new fixed points, which are very far from the equilibrium plane. And which, I mean, if you analyze the critical behavior at these fixed points, I mean, you get exponents that are really different quantitatively from the equilibrium critical exponents that you get here.
Excuse me, so here this plane is the equilibrium plane.
Yeah, exactly.
Then this direction is which coupling does this?
I mean, this is now the one of these, the GC is, it's one of these couplings here. Yeah, so all I need to say, I mean, we have, I think, running 10 couplings. I choose just a cut here. I mean, where we have this situation, and you can trust me that it's one of these couplings. It's not a single coupling, it's basically ratios of couplings. Yeah? If the ratio of all these terms in HC and HD is not everywhere the same, then we break it. Yeah? So we just have to make sure then we get a direction leading out of the equilibrium surface.
And how, so there are many other couplings, but they're all irrelevant at these fixed points?
This fixed point has is a infrared stable fixed point with a single relevant direction, and then so it's all, in that sense, all as usual. But I mean, the universal behavior is different because we have a different symmetry, yeah? So we have not the equilibrium symmetry.
Can I understand it as basically not thermalizing when you coarse grain?
Exactly.
Under coarse grain.
Yeah. That's a good picture. I mean, that was this what I mentioned here with some systems flow to equilibrium. That means at asymptotic large distances, yeah, you see again emergent the KMS symmetry, if you like. So this can be an emergent symmetry, and that's a usual thing. But here we see there can also be circumstances, yeah, which I feel is pretty intuitive, yeah, when we have the onset of a time crystal. And so that you really see non-equilibrium in your face, and that tells you, yes, then you can have a different universality.
And
what's the upper critical dimension?
4, as usual.
For space.
For
plus the
space.
time.
For space.
And the phase you get if you do add this relevant deformation is things blow up, or what happens?
Sorry?
If you start from your fixed point and add the
Right,
relevant...
that's the next slide. Yeah. So there is a very interesting phenomenon from my view. There is a kind of spontaneous breaking of equilibrium conditions, indeed. Yeah. Meaning that if I initialize my RG flow on the microscopic scale somewhere here, yeah, then the system wants to flow to this equilibrium fixed point, but at some point senses this relevant direction and departs. Yeah? And in which sense this compares to spontaneous symmetry breaking, and there's a non-commuting limit. If I first send equilibrium perturbation to 0, then do my calculation, I will reach this fixed point. But the tiniest perturbation, finite perturbation, will always activate the flow to this new fixed point. Yeah? So, and this is actually, I would say, it puts a caveat on some models. Yeah? For example, this group here, ON cross OM, more generally, has been discussed for the physics of incommensurate magnets. Yeah? They have a kind of wave in space, and that gives rise to this SO2, not because of time periodicity, but because of space periodicity. What this analysis here tells you, that probably this fixed point is not very relevant physically. The one that you get from stat.mech is not stable, yeah, but there can be, in fact, situations where, I mean, when you put the tiniest non-equilibrium perturbation on an incommensurable magnetic phase transition, then you will also activate this flow without even driving it. Yeah? So because of this spontaneous breaking of equilibrium.
Sorry, but I meant there's an extra relevant direction, right? Let's say towards us, which goes away from your fixed point.
Mm-hmm.
So what happens there?
I mean,
What's the phase?
so this I try. So here is, I mean, there's one. So this is attractive, yeah, and then there is the relevant direction that goes out there. Mm-hmm.
But if your fixed point has no relevant perturbation?
No, it has. I mean, it's just not plotted. I mean, this is just a line that goes from. I mean, I would.
How many tuning parameters do you need to see your fixed point?
One.
One. And what happens if not critical, but what kind of phase is it? It's out
I
of
mean,
equilibrium?
then you,
Would you call
this
it-
fixed, yeah.
Would you call it equilibrium phase or non-equilibrium phase?
Yeah, let me put it like that. I think it's, I mean, if you are exactly at equilibrium, yeah, then you get a normal.
I'm
But if
asking
you
about,
start
we're out of
slightly-
equilibrium, but you detune. Out of equilibrium, but let's detune.
If you start close to n plus, where do you flow?
Maybe here's Gaussian, this is Fischer. So we have this. Yeah, so, and then there's something in the plane that goes out. So now you want to be here.
No.
So this is equilibrium still.
Yeah, that's right. So this is the equilibrium plane, right? So there's a runaway direction, which is, will bring you to some equilibrium phase if you tune away. I'm asking about what that phase is in the non-equilibrium context.
So that is our rotating.
Okay, it's back to the, I see, to the kind of ordered, what you would call the ordered.
Yeah, so this is kind of the order. It's the onset of a time crystal. I think, or maybe what is the following thing is confusing.
Okay,
I was
think it-
thinking. So here is this non-equilibrium direction. I'm thinking of systems, maybe they are initialized here. They already quite strongly break this. But I'm not saying it's impossible to operate the group of n cross SO2 under equilibrium condition. So that's what people do in these incommensurate magnets. And then they analyze it with StatMech, and they characterize this fixed point. But the static formulation of the problem kind of projects out the possibility of this runaway.
But I guess, so these incommensurate magnets exist. Do they see this physics?
I mean, of course, there is a kind of, this can be the size of the universe if you're very, very close to equilibrium. I recently talked to, a very good Russian guy. He told me, I mean, they are looking at some incommensurate magnets, they see critical behavior they don't understand. So, I mean, I think, maybe one has to be also aware of this effect. But one thing you can trust me, this is epsilon expansion. Yeah? So all these fixed points are close to the Gaussian one. So there's a systematics in this. Yeah? So it's not a plain guessing. Yeah? So
there's another annoying thing with magnets, which is that the cubic breaking O3 to cubic group is relevant. And so there's a, so I guess there's an extra,
nature is more complicated. Yeah? So, but as a matter of principle, I mean, I think it's worth being aware. So that there can be some systems that under the tiny, there's another example, like KPZ is also like this, but that's really the only other example I'm aware of, where you have the spontaneous breaking of equilibrium.
Sorry, I'm still slightly confused. Where is the time crystal on this phase diagram?
Well, I mean, this is not the phase diagram, yeah? So this is really the critical, zooming into the critical point. Yeah? So if you, no, but I put you the phase diagram. Basically, we are really analyzing this line, where this is disordered, and we have the direct transition into the time crystalline
So we've tuned ourselves to the critical line within
Exactly.
within that critical, the parameter space corresponding to that critical line we're talking about RG flows.
Exactly. So this is really the critical line for the onset of a time crystal. And the fun point is this emergent symmetry that forces us to really do a different calculation. Okay, so now, I mean, how, if you had the perfect system doing this, yeah, so then how could you see that? And I mean, a kind of smoking gun goes via this fluctuation dissipation relation. Yeah? So if you have a system held at equilibrium, then fluctuation dissipation theorem tells you a rigid relation between response and correlations. And in particular, in that case, yeah, you say in a detailed balance, all subsystems are in equilibrium with each other, meaning that they have all to obey the same temperature. Yeah? So, and these, for example, the subsystems could be momentum shells in an RG way of thinking. Yeah? So all the momentum shells have to the same temperature. Temperature is Q independent. Out of equilibrium, you can still, I mean, relate dissipation and fluctuation, but you're not guaranteed that this function here is momentum independent. And in fact, if you do the calculation, you see that this effective temperature would even diverge in a universal way, governed by the exponents that are showing this, that are related to this new fixed point. And that is observable, for example, in the anti-Stokes measurements of spectroscopic probes. Okay, so yeah, so I think it's taking a bit longer than expected. I could now either discuss this, basically the physics of this phase here in there, where basically, I mean, we analyze the Goldstone modes of the broken time translation symmetry, or I could alternatively switch gears and move to this, I mean, maybe to quantum effects. So in developing an analogy to this directed percolation scenario. So any hints from the audience what I should do?
Well, I'd like to hear about the fermionic stuff.
Okay.
It's what I think you described in your abstract.
That's excellent point. Excellent point. That makes this choice simple. Yes. And right. So here, this is no, really switching gears with a PhD student Rohan Mittal, clinical master student Tom Zander, postdoc Johannes Lang. Okay, so let's think about this classical active matter scenario, a completely different one from what we've seen. That is absorbing state transitions, and a classical absorbing state transition, that is this wetting transition. Yeah? So you can think of, this is a system, a one-dimensional system developed over time, and we just pour some water into the system, and then in the long time limit, you can either reach this absorbing dry state, or you can get a wetted state, yeah, where all the sides are occupied. Yeah, so, and in between, it's a critical state. This is the absorbing state phase transition. Okay, now in terms of physical processes, yeah, we can describe the system as follows. There's very simple dynamical rules. So a particle, yeah, can either evaporate, or a drop of water can either evaporate with a rate gamma, or it can branch. Yeah, so then, I mean, you get, I mean, a process that continues this wetting phenomenon. What you cannot have is an offspring from the vacuum. Yeah? So it's also, I mean, useful to think about this as infection dynamics. There has to be an infected individual to branch, yeah? Or it can just recover this individual. But what you cannot have, if everyone is healthy, then you won't have a disease. Well, some approximate simplicity of physicists. Yeah. Good. And then the phase transition in this problem is from an inactive to an active phase, where basically you track the order parameter in this problem is the density of active sites. Yeah? It's a very simple problem. There is now two things I would like you to basically take out in a zoomed out way, namely this absorbing state here in this precise example is an uncorrelated empty state. Yeah? There's not a single particle in there. So that's what you would refer to, I mean, maybe in high energy terminology, that's a trivial vacuum, obviously, by all standards. Yeah? And then the second interesting thing is that also here you see with the naked eye that this is an out of equilibrium kind of dynamics, because this process here of annihilation does not have a reverse process of creation. That would be always like that in a system with detailed balances. All the processes have to come in reversed pairs, yeah? So that's the hermeticity of equilibrium dynamics, so that is certainly breaking detailed balance in a very strong way. So now let's think about the critical behavior of this problem. So we can again go by this kind of plot here, thinking from the microscopic models to what is actually the physics of the phase transition. And all these, I mean, or let's say this wetting transition, to be specific, this is in the so-called directed percolation universality class. And there is a conjecture by these gentlemen here that posits that all absorbing states, yeah, with a few caveats, of course, yeah, are in this directed percolation universality class. So it's a very strong fixed point, again, of the non-equilibrium nature with no detail balance on the microscopic scale, and that does not recover. So, and that means, yeah, so that you have a gigantic number of different physical setups, yeah, so that are in the domain of attraction of this class. So it could be this water wetting phenomena, epidemic spreading is in this class. Also, people have engineered Rydberg systems, Rydberg atoms in the dissipative regime to tune them basically into the domain of attraction of directed percolation. People have used trapped ion quantum simulators to see this, and even this phenomenon that Romain spoke about yesterday, measurement-induced phase transition, map to this classical directed percolation problem under some circumstance. And so, the upshot, if you coarse grain these different physical systems, you end up with this directed percolation field theory where, I mean, this is totally innocent here. Yeah, so this is an MSR type action here with a noise field and a deterministic field here. This is the quadratic part, and then the interesting part is this cubic interaction, so that violates this equilibrium symmetry, but obeys another interesting so-called rapidity inversion symmetry. But that's the field theory for this problem. And if you analyze this critical behavior, so then you get a non-equilibrium universality class, meaning that the detail balance is not recovered at the macroscopic scale. And we take home here that even quantum problems can map to this classical directed percolation. So it's not obvious just starting with a quantum system that you get, I mean, a quantum critical point or something out. So there is, on the other hand, I mean, quantum systems might allow you to give very clean realizations of this, but I mean, still, it remains a bit a question, can we get, I mean, problems that are similar to this directed percolation setting, and in this way, get some universality that is out of this fixed point.
Quick question, how should we think about entropy as I undergo this phase? Is it like one of these entropy decreasing processes?
No, yeah. If you want, So that maybe I can come back to this question more in the quantum realm. So there you, but it's true. You can, I mean, if you are on your way dynamically to this fixed point, I mean, I think you should look at it like that. If you're in this inactive phase and you start your system at some finite activation density, then you will see indeed this density is gone. So you end up with a vacuum state, and that, of course, has zero configuration entropy. So because it's an empty, think of an empty lattice, zero configuration entropy, trivially because there's only a single configuration. In a quantum system, the analog would be a pure state with a single component in the density matrix with a single spanned by a single wave function, also has zero entropy then in this sense. But in this regime, of course, you have entropy production, if you like. So you can look at this transition also as a zero to finite entropy phase transition. That's totally effective. Think zero configuration entropy, the notion of entropy that works in the classical system. And it's kind of a viewpoint on this transition is that basically this, you can see from these dynamical rules, so that the absorbing state is present everywhere across this transition. It's just this is a regime where it's dynamically stable and reached. Here it is dynamically, it's present but dynamically unstable. So system goes away from it. So it's a kind of dynamic phenomenon. So that the dark state, or this absorbing state, needs to be present everywhere. Okay. So now let's go into the quantum direction, and then we need the concept of this Limblad equation. I think it was also mentioned. So it's basically describing the time evolution of a system density matrix, which can be generated by a coherent piece, just a Hamiltonian, and also this driven dissipative piece, which results from tracing out environmental degrees of freedom. If you want to interpret this a little better, so then you can just rewrite it and incorporate this anticommutator term here as the imaginary part of a Hamiltonian. So then this describes basically energy minus dissipation. And again, like in the classical systems, we need to preserve probability. So therefore, we need some fluctuation term that compensates for this dissipation. And this, with this factor of 2, ensures exactly the probability conservation of this problem. So that's how you can memorize maybe these prefactors here. Okay, example, this comes from quantum optics, so maybe a driven two-level system. Yeah, so the Hamiltonian in this case is just that they're tuning the distance of the laser drive, yeah, and the laser intensity gives you how these levels talk to each other by coherent dynamics. And then the Lindblad operators that result from coupling this small system to a dissipative environment, to the radiation field, will just describe you spontaneous emission. And also, yeah, I mean, if you look at these Lindbladians from a field theory perspective, and this is second quantization, but you rewrite it as a path integral, and then you also see that these will violate KMS symmetry, yeah, with the basic physical idea that, I mean, you couple the system to different bases, yeah, and this just doesn't know to which base to equilibrate. Yeah. So each of these Lindblad couplings here, you can think of it as an independent path. So the system is confused where to thermalize. Now comes the analog of this absorbing state, dark states. So this is states that are annihilated by the full set of Lindblad operators and are at the same time eigenstates of the Hamiltonian. So once these conditions are satisfied, yeah, so then you see the time evolution will stop. Yeah? So we reach a dynamical fixed point, yeah, for this circumstance when the density matrix is this d outer d. And it becomes particularly interesting when the dark state is unique. Yeah? So that would mean, I mean, you have to check that, yeah, whether you have a situation in which basically there's only a single point in Hilbert space, yeah, which is dark, and there's no situation that the system can get trapped in Hilbert space and cycle around. A unique dark state, you have to make sure that this is the case, that is really analogous to the absorbing state in that sense that once you enter it, you cannot leave. Yeah? But it doesn't tell you that you will reach it. Yeah? So in finite time. Yeah? And that leads then to a directed motion in Hilbert space, yeah, where an if this uniqueness is given, arbitrary density matrix thins out to a pure state. So indeed there we have this circumstance that, I mean, this has some finite entropy for normal entropy, and you go to a pure state which really has zero configuration of entropy. Okay, simple example, yeah, would be that, I mean, a trivial example again, that this Hamiltonian is A dagger A, and it's just a harmonic oscillator, and this, it just empties out. The Lindblad operator is just describing decay. Then you get a trivial dark state analogous to this classical absorbing state, but it can also be more interesting. Yeah? Suppose you have these operators here, they commute with total particle number, and if you analyze this problem, you can see that the dark state for these guys is actually a boson, condensed boson state at a finite particle number. So fixed number BEC, yeah, you establish by dissipation, you establish phase coherence of a BEC. And if you interpret these guys as fermionic creation and annihilation operators, then finally the system goes into a paired BCS type state at a fixed particle number. For this 1D example, it's actually the fixed number version of the Kitaev chain that these operators pump into. Yeah? And that is what I want to understand now as a non-trivial vacuum state, yeah, which is not particle empty, and in particular, yeah, so a BEC or a BCS superconducting state, they are also quantum correlated. So, and that sets the stage for looking into this quantum critical phenomena. So first, we need to build basically the target state. Yeah? So what is our non-trivial vacuum state that we want to analyze? And here we choose a dissipative chiral topological insulator. It can be done in d dimensions, but let's, for the sake of explanation, focus on 1D. So then the chiral topological insulator is just a two-band SSH type wave function. Yeah? So that is our targeted dark state, the non-trivial vacuum. And then we want to, so the lower band is occupied, upper band is empty. Now we want to find the Lindblad operators that hammer the system into this state. And so, I mean, just to say, I mean, this state is quantum correlated. For example, if you look at the winding of this, there's a non-trivial winding number. You can dial in a non-trivial winding number into this state. Yeah? And now, let's think about the parent Lindblad operators that push us into this state, cooling into this vacuum. So that is the proposal. Again, they conserve the number of particles, but they just shuffle around the superposition of particles, and they afford an if-then interpretation. Yeah? So if, namely, if the upper band is empty, yeah, So then this operator evaluates to 0 because it's already empty. If conversely the lower band is already occupied, then by Pauli principle the L2 dagger evaluates to 0. So also then the dynamic stops. So if the upper band is empty, if the lower band is full, then the dynamic stops. Otherwise, if this condition is not yet met, the dark state condition, then these guys will just reshuffle the superposition and create the particle somewhere else. Okay. So the idea of looking at a phase transition in this problem goes as follows. We now look at two operators L plus, L minus, with each of which stabilize a state with a left or a right winding. Each of them gives us winding number plus or minus 1. And now we set them in superposition. In this Lindblad operator, we build a superposition of these operators so that when these guys balance, the system remains undecided into W equals 1 or plus or minus 1. And that is what happens. So these are the extremal points with winding number plus minus 1. And then the winding number can only jump. So there must be a point, and exactly when cosine and sine balance, where the winding number jumps. At the same time, at this point, when you analyze the problem, you see that the damping gap closes, and the purity is unity across the entire transition. So this realizes really the analog of a pure state quantum phase transition. So we are guaranteed in this construction to remain in a pure state of fermions. Okay. And it is a transition between two non-trivial vacua. So a little bit different from this directed percolation, where we went from a trivial absorbing state to an active state. Here we're going between two but topologically distinct absorbing states. And I mean, we are dealing with an interacting Lindbladian, so we really have to look at this behavior more carefully. It's not just a quadratic problem. And so here is our approach. We start from this Lindblad equation. We map it into a path integral formulation. Then we do a Hubbard-Svratonovich decoupling to derive the near quantum critical action. So we really compute the coefficients of this mesoscopic action here. That allows us to identify the relevant degrees of freedom for this quantum phase transition. And based on this effective model here, so we take this step here now more seriously, then we run an RG and identify the critical behavior. Right. So this is this near critical action, and a few aspects are worth stressing. So you see here it's a kind of cubic Yukawa coupled theory where the fermions chi here speak to bosonic degrees of freedom, and those bosonic degrees of freedom are just the conserved particle number, diffusive mode of particle number conservation. And so if you do this in d dimensions, so then it has all the properties of a Dirac model with the chiral symmetries and odd dimensions. The interesting point is to compare the nonlinearities of this directed percolation, which are cubic and are purely bosonic. Now here we have some very similar structure, namely some bosonic degree of freedom coupled to fermions now, which is really, but which have the same structure. If you forget about bosons, fermions, and then it looks really the same thing. And the bosonic modes are the hydrodynamics of particle number conservation, and this model has a lot of symmetries, namely a chiral symmetry and basically spin rotations in d dimensions and spatial reflections, which is crucial for the following thing to happen, for a new symmetry to emerge. When you have all these ingredients together, you don't need the microscopic theory. You can just write down this model, and then you will see there is an interesting new symmetry in this problem, which is a parity symmetry of an anti-unitary type. It involves also reversal of time, and I tell you that this kind of transformation here leaves the action invariant. So this is really derived just on power counting and these symmetries, and microscopically, we did both. But the interesting point is this symmetry guarantees that the quantum state remains pure. So this is a symmetry principle, so that protects the purity of the state in the following logic. We have a word identity from this symmetry which connects fluctuation, dissipation in this way. And if this is the case, you can immediately conclude that the equal time correlation function of fermions obeys the condition that you know from a pure state. So it's a symmetry that implies, by a non-thermal fluctuation dissipation relation, guarantees the state is pure. The second implication, it also constrains the RG flow. Yeah? Now think of this as a manifold, or this is the space of parameters that any action can have, any of this type. But now we have this additional symmetry, and then you stay on a certain manifold, yeah, and it excludes a relevant direction sticking out of the plane to be activated. Yeah. And then in this way we can compute the fixed point for this problem and extract the critical exponents, and done in a second. And so, and I mean, that characterizes now a kind of absorbing state phase transition. Last point I want to make. So this fermion have now this dark state symmetry, and that relates actually to two different problems, namely quantum criticality. Can be also looked at symmetry protected by this KMS symmetry operated at 0 temperature. So that's what protects purity in this case. Absorbing state transition have a rapidity inversion symmetry, and all of them basically are of this reminiscent of time reversal and protecting the purity of the state. So, okay, I think, thank you very much.
Okay, maybe one quick question. There were already a lot of questions. If not, then I guess we go into.
Actually, no, I'll ask a question. An experimental question. So you mentioned the exciton, polariton, and there were several options for the symmetry. How do they act?
There's several options.
I think in one of your early slides you had either U1 or U1 times U1.
Right.
How do they act in the...
So they can have a, I mean, basically these are the excitons, they're coming from fermions. Yeah. So there can be an SU2. Okay. But actually some people look at that, yeah, but usually, I mean, you look at, I mean, only a single polarization degree of freedom. Yeah? So that's an experimental thing. So the SU2 is reduced to U1. So in principle, there could be an SU2. Yeah? So
and then there's an extra U1 from driving from this.
Right. You could say the SU2 is gone completely. Yeah? You have to pick a single polarization degree of freedom. Yeah. So and then you can say maybe I have the diagonal of this. You get an additional Z2 tensored in. Yeah. And so and in principle, there's nothing that would forbid a U1 cross SU2 in these systems as well. But the U1 is really quantum mechanical U1. And the SU2 is fermionic SU2 spin.
Just before we thank Sebastian again, so the hotel needs a rough estimate for how many people are having lunch here. So could we just raise your hand if you're having lunch here? I'm not counting the sandwiches.